to Revolution Against Evolution. I'm your host, Doug Sharp.
Your co-host, Rich Gear, here as well, and we have a great guest on us who's going to talk about a lot of things, well, specifically radiometric dating. Doug, what's the title of our show?
The Broken Clocks of Deep Time.
And our guest name is?
Charlie Wolcott.
Wolcott, right.
Charlie is joining us from El Paso, Texas, and he is a physics teacher in El Paso, Texas. And so, Charlie, I'll let you introduce yourself, and since you're a physics guy, I presume that's why you've chosen this topic about radioisotope dating. And the first question I would ask you is, why is this important for a person who is proposing biblical model?
Okay, I would consider radiometric dating to be one of like the major pillars of deep time, of evolution, of the origins model that is in defiance against what the biblical record has given us.
And when you say deep time, you're talking millions of years. That's what you mean when you say deep time.
Millions of years, regardless of whether you accept biological evolution or not.
Okay.
And so the geologists tend to use this as a validation for their particular geologic column that they propose. Now, we as creationists have a different model, is that these layers of rock with their fossils in it are buried. The fossils in them are buried according to their the way that where they were deposited during the Noah's flood. But the geologists, the standard geologists, or what you would call the
deep time geologist, the secular geologist, if you will.
Their preferred term is conventional.
Okay, conventional.
Yeah.
It is their preferred term.
I call them convectional because they're cooking up something that's not right. Anyway, all right, fair enough. And we got to ask you the question of why this is important, and you're going to get to that because we're not going to totally turn the show over to you, but pretty much we are, because you have a lot of good stuff. I've seen your outline, and it looks really interesting because it is very important to the debate, to the origins debate, and. Because if you don't have deep time or long millions, no one has ever actually seen evolution occur. And so they need lots of time to give you that space for it to occur. And one of the big arguments, of course, is the radiometric arguments. I also would like you to explain a little bit. We've done it on our show before, but we'll put it together. There's quite a fundamental difference between the deep time arguments and the carbon-14 arguments. It's quite a different type of dating, but they conflate the things together. I hear people talk about carbon-14 when they're really talking about something like potassium argon. And so if you would get into some of that stuff and what are some of the problems would be great.
So they're broken clocks of deep time. Okay, so as we mentioned, okay, radiometric dating methods are a pillar for the atheistic faith. Okay. And what these give us are the hard numbers, according to them, that prove the Bible's history is not reliable. Now, this is primarily on the atheist side of things. There are a number of older creationists who use these methods, but they say this going for the glory of God. And I'm not quite sure why they use a secular, non-biblical driven idea to show that's what God did, but that's another story. These are cited; they're basically cited as unquestionable facts. Yet after their public use has been going on for a while, we younger creationists have been discovering more and more problems with these methods. This has been this topic has been a personal project of mine for about 7 years now, kind of on and off, mostly because of my job. So I haven't been able to give it the time I want to give it. But I've been doing a mathematical analysis on these methods, and the more I've been studying, the more I realized. I'm realizing and seeing that these are result of a propaganda and an agenda, rather than actually being authentic scientific study.
Well, I did want to mention that I studied this about 1970 or 71, something like this. I took a class on radiometric dating when I was in my physical science degree. And one of the things that happened during that time is I discovered these things that you're about to bring up here. And I was writing a paper and presenting it to the geology professor. And he didn't like my paper. He required me, he said to me, if I wanted to grade, I needed to rewrite my paper so it presented both sides, or to present it from the evolutionary point of view. And so I said, well, I guess if I want to grade, I guess I can write some fiction.
Oh, okay.
But it was a little bit of a disheartening thing that to present some of these things, and you can tell that even in 1970, that's 50 years ago, that's these issues still hold up as being problems for evolution. And so I'll let you get into those.
Yeah. Okay. So as I've done my studies, I've predominantly looked at three of the big deep time methods: uranium to lead, potassium, argon, and rubidium strontium. And when I started working on my analysis, one of the things that stood out to me was on these dating ranges, these three deep time methods tend to stop at 4,600 million years, or 4.6 billion years. And that happens to coincide with the age of the Earth. And that kind of struck me as interesting because theoretically, these methods should be able to be datable for well beyond the age of the Earth if they are reliable dating methods. And so I'm like, why are they reporting that the methods are limited to the age of the Earth? And what I'm seeing is that, and as I've studied more and more and more, what I'm seeing over and over again is the dating methods adhere to the story of deep time and evolutionary thinking a lot more than they do actual science. And of course, the defenders of these methods will say it's the opposite. They're like, no, we're making our story based off the evidence. And I'm like, the stories that we're getting don't reflect that. Okay. And then, of course, carbon dating, carbon to nitrogen, and that's a completely separate animal. Okay, not only because of its much short half-life and range, but for a number of other factors too.
Yeah, for those who don't understand what a half-life is, do you want to kind of explain that a little bit? So before we go too much into it.
Well, I'm actually going to do that in a second here.
All right, good.
Okay, so we're going to look at the exponential decay function, and that's going to be the focus of my talk today. So the standard exponential decay function is n equals NO e to the negative KT. And for those of you that are not math people, that might look like Greek. And when you're dealing with physics, a lot of it literally is Greek. Okay, but n is the number of parent isotopes that's currently remaining. NO is the number of original parent isotopes of when the so-called clock was set. And we're going to look at these in more detail. K is the decay constant determined by the half-life. Okay, so here we can look at the half-life. When we're looking at these dating methods, the different isotopes are different elements have a certain number of protons that make the nucleus unstable. And so over time, the nucleus will break down into a more stable system. And what scientists have done is that they've measured how quickly these decays take place, and they calculate the half-life. And the half-life is the amount of time it takes for half of the substance to decay.
Now, I find it interesting that the half-life of uranium-238, which is the first method, is actually the age of the universe.
Age of the Earth.
Age of the Earth, yeah.
Yeah.
That could be just chance. It could be just chance. I'm not going to put a conspiracy idea on that one. But I do find it interesting that one of their favorite methods happens to have a half-life of the age of the Earth. Okay, and then what everyone is looking for is T, which is the age of the sample. Now, what I'm going to do today is that we're going to go through this equation, and we're going to look at how each part of the equation is derived. And I'm going to indicate there's a number of problems with that. So, key assumptions with this decay equation. Okay, we have to know the initial amount of parent isotopes. Okay, we have to know where we are on the graph, where it starts. We also have to know the initial amount of daughter isotope. Okay, because again, that determines the ratio that we're going to be using. Okay, in order to make the math work. We have to assume a constant decay rate. So in other words, nothing can alter the rate of decay. And so we'll look at that. It also has to have a closed system. In other words, you can't have isotopes leaching in or out. Okay, otherwise that's going to create problems, and the data is going to be skewed. Okay. Now, throughout the young Earth creation literature, each of these assumptions are pretty well documented and addressed. Okay, so I'm not going to cover those in extreme detail today. But a fifth, more subtle assumption is homogeneity. In other words, that each of these isotopes are uniformly or evenly distributed throughout the sample.
Okay,
and that's also critical to make sure that you can account for that. Now, the only one of these things that can be directly measured is the homogeneity, but to my knowledge, there hasn't been very much a test that demonstrate that that's usually the case.
Now, I wanted to point out that a lot of the things that you're using in your arguments come from this book, The Mythology of Modern Dating Methods by John Woodmorapee. Now, we had a chance to interview him back at the time when he wrote this book.
Yep.
And he's quite a character. We appreciate it very much. But he is a very meticulous researcher.
Yes.
In fact, his references take up about half of his book. So he supports his stuff very well.
Yeah, he's a very thorough researcher. He leaves pretty much no stone untouched. When we're looking at this equation, the number of current parent isotopes is the only thing we can directly measure, and we can measure in terms of like parts per million or parts per billion. According to Vernon Kupps in his Rethinking radiometric dating methods, at least with carbon-14, we can measure up to parts per quadrillion. Okay, so the technology is getting better in terms of our ability to measure isotopes.
So what you're saying is the only thing we can really study or measure is what we have in the present.
Yeah, directly, yes. That's the only thing we can directly measure in the present.
The rest of how much parent element there was at the beginning, how much daughter element there might have already been there at the beginning, you can't really know that, but there's assumptions made.
Yeah, we cannot directly measure that.
Okay.
The original amount. Okay, this is supposedly when the clock is set. And each of the methods have their own little technicalities as to how this is determined. With potassium argon, one of the key factors is a requirement for there be no argon in the molten lava, because that's what determines the clock. Yet the literature is full of references of excess argon in fresh lava. Which kind of refutes the entire system, but they keep using it.
Yeah, why is that?
Good question.
I wondered that for years, because it seems to be the potassium argon, it has the most obvious possibilities for error and for mistakes to be done. And in fact, there seems to be physical evidence based on what you're saying, modern lava, which has argon in it. How do we know the ancient lava did not have argon in it as well? There's too much of this kind of stuff going on. We also have dates in recent lava flows have dated millions of years old, and we know it's less than 50 or 100 years old.
Yeah, lots of cases of that. And what we see is not scientific testing to go verify the results. What we're seeing are a bunch of excuses. There are two primary ways we can indirectly measure the original amounts. Okay, that's what the scientists are saying. We can use the current daughter isotope to find the ratio of parent daughter, or we can use the Isochron method. So if we're going to try to count the original parent isotopes, we have theoretically we'll have a sample of pure potassium argon. After one half-life at 1.3 million years, half the sample becomes argon, half the sample becomes potassium. After 2 lives, it's 3/4 argon, 1/4 potassium. That's the theory. So you could determine, if you know that you originally had pure potassium and no argon, you could determine how much potassium there was by how much argon there's currently present.
Which is problematic at best, right?
And that's wishful thinking. Is that's I think that's too generous.
Isn't that kind of the problem with all the dating methods?
Pretty much.
Okay.
In order for this to be true, you have to assume that all daughter amounts are radiogenic, that they're a result of radioactive decay, and you have to know that what the original amount of daughter isotopes were, and you have to know, and there can't be any leaching in or out, or you have to be able to account for precise leaching rates over millions of years, which I'm like, good luck. So that's one way that they approach it, and the scientists are trying to lean away from that. They're instead going to Isochron methods, okay? And so because this one's really complicated, so I'm really just going to scratch the surface. They try to account for not knowing the initial values by just looking at parent-daughter ratios. And then but when you do the mathematical computations and transformations, you get a pair of linear graphs, and the radiogenic pairs show a gradual change from the non-radiogenic pairs. Okay, that's the idea. And these are claims to be the best, most reliable methods. However, for time's sake and just where I'm at in my research, I'm not able to discuss this in great detail. But Vernon Kupps, in his Rethinking Radiometric Dating, it's just radiometric dating, not radiodating methods. He cites 4 assumptions, okay, and they happen to be very similar. Okay, the rock system has to be closed the entire time. In other words, no leaching. You again have to know the initial daughter isotope values. Okay, and these methods tend to assume that they're supposed to answer this question, but instead they actually assume it. Decay rates have to be constant. And then again, the homogeneity question. Kupps suggests here is that these require universal and even distribution of just the daughter isotopes, but doesn't require it for the parent. So that's something I have to look into more detail to kind of figure out what he's really talking about. But these are the assumptions that Vernon Kupps of ICR goes into in Rethinking Radiometric Dating. Measuring the decay constant. Okay, this is actually the most important part of the equation, but it's the least questioned, even on both sides. One thing I've seen from the big young Earth creation organizations, they tend to not question the measured decay rate. And my studies have made me question it.
Wow.
Okay.
Well, I thought that the RAID team talked about accelerated decay was one part of it.
Yeah, they do talk about accelerated decay, but only for in special circumstances, okay, such as the flood. But part of it but beyond that, they do tend to suggest that the half-life measurements are pretty accurate. Okay, I even heard Jake Hebert even made that claim during a conference here in El Paso 2 years ago. And in my studies, I'm like, study a little bit closer.
So they're saying that the long dates of some of these radioisotope dating things have been because of accelerated decay. I've heard at the creation as well as Noah's flood. It caused decay to accelerate. I never quite fully understood why that would be. Maybe the creation I can understand, different processes involved. The flood I didn't really quite understand it as far as that goes. But you're saying that in itself is questionable.
Well, I can give you a little bit of an example of that.
Yeah.
If you have a radioactive element and it all of a sudden decays, okay, into something else, well, that now becomes the daughter element, but you still have remaining these non-decayed parent elements still sitting around here, and they still sit around there for all these years and years and years and years and years, and they don't decay. And the question is, how can we actually determine over these millions of years if the decay constants are true because we really don't know what the over the long life of this.
We have to assume a constant decay rate, but when I've studied the Geiger counter and the liquid scintillation tools used, okay, that's something that not many people do. Is like how are these things measured? What I've kind of noticed, I have reason to claim that the constancy of the decay rates that's being claimed is due to the system, not due to the actual physics.
Oh.
And I don't have time to go into that today, but that's some of the things that I've been looking at. And of course, the rate team has suggested evidence of accelerated decay. Okay, I'm gonna have to skip this one, but Vernon Cups suggests that the variation in the decay rates can value by factors up to 1 billion.
Wow.
Yes, I've seen that.
Yeah. Okay, and that's from Rethinking radiometric dating. But are they accurate? Okay, so when I did some research on how the Geiger counter is used and how this stuff is done, I came across a college lab manual where they determined the half-life of potassium 40, and the manual cites a paper that reveals a 20% efficiency rate, thus requiring an 80% fudge factor being introduced into the half-life calculation.
Whoa. So
I'm like, okay, that requires me to need to look at deeper into what's going on here. If there's an 80% fudge factor they have to introduce.
Yeah, I think the fudge factor has a lot to do with why they can get the Isochron dating method to actually give them consistent results. Because they can fudge all those assumptions.
Yeah. Now, according to the lab, they only observe things for 30 minutes. So if you only observe one sample for 30 minutes, this is how much of the half-life they're observing. 10 to the negative 12th of a percent. 10 to the negative 12th of a percent of the half-life. 10 to the negative 13th of a percent of a half-life. And I'm thinking, like, that's not enough sample space to make any kind of claim.
Yeah, that's a good point, because I've always wondered about that, how they can measure the decay. I mean, obviously no one can measure 4.6 billion years.
Yeah.
They can't measure 47 million years. How they must take a small little piece of time and see what happens during that particular period. Is that what you're saying happens?
Yeah.
And it's a very small, virtually almost non-existent period of time, and they're extrapolating outward all this other time.
Yep,
Okay.
that's what's happening.
All right.
Okay. Now, in the original research, they would have observed for longer than 30 minutes, but are they running their devices for longer than a couple hours? Probably not, and they're changing out their samples frequently. So again,
It's expensive to do a radiometric date.
Yeah, well,
$500 for each date, and
yeah.
so their time on the machine is limited.
And leaching is a big issue, and we've been mentioning John Woodmarap's mythology and modern dating methods, and he cites numerous papers where leaching is indeed a major problem in each of the methods. Okay, and one of the big points that he makes is because many of these methods depend on an unstable alkali or alkaline earth metal. Okay, potassium, rubidium are two of the big ones. These metals are easily interchangeable in their compounds with other metals of the same column. Okay, and what's interesting is that the studies have shown that these interchangeabilities happen at relatively low temperatures, so you don't need hot magma, and they happen in aqueous solutions. Well, we have those kind of situations in the thing called the flood.
Yeah, if you have water action, the potassium ions are more soluble in water than the argon, but the rubidium is more soluble.
Well, argon is a gas. It's an inert gas. So
you see, rubidium is more
rubidium and strontium. Those are alkali and alkali earth metals.
Yes.
and rubidium is more soluble than strontium is. You're saying, right?
And parent elements are rarer than the daughter
And
elements.
the rare. Well, it's also, you said years ago. I mean, even uranium salts could be leached off by. So this is something I didn't really understand. Doug explained to me a little bit last week. There's being like leaching is a chemical, right? It's a chemical response as opposed to actual decay rate change. It's something different.
And the bulk of the defenses are, as we're trying to look at this scientifically, they're defending it with bad logic, bad storytelling, bad excuses. And so what I say is, math never lies, but wrong equations do. And so, so if your calculator is programmed to say 2 + 2 = 5, and you use that for your entire career, you're going to think that you're getting good results, but it's fundamental. But the calculator has been fundamentally wrong the entire time, and everything has to be re-examined. Just a couple of resources: Rethinking Radiometric Dating, Rethinking Radiometric Dating by Vernon Kupps, Thousands Not Billions, which is about the Ray Project and the mythology of modern dating methods. And then I'm Charlie Wolcott. I'm a blogger, speaker, and author for the Ministry of Worldview Warriors. And there's my contact pages.
All right.
Sounds
Well, we really appreciate you being on our show, Charlie, and
Thank you for having me.
I'm glad that you are doing this and teaching your physics students this, I presume.
Not yet, because we don't cover radiometric dating methods in my classes yet.
Yeah.
I'm trying to get my class to get AP Physics 2 going, and then I will.
Well, that'd be great. But if we can make this available to people to study, this is and to learn about the assumptions of the dating methods, you can believe that the Bible is true and the Word of God is true.
Yeah. Well, yeah. So I didn't get a chance to explain that, but what I'm doing is a mathematical analysis on these methods,
Right.
From an angle that no one else has done before. Okay, and I really mean no one else has done it before, because I've asked the YC orgs and Charles Jackson in particular. He used to be with Creation Truth Foundation, and he's like, he thinks I might be onto something here.
And we'll see you next time on Revolution Against Evolution.
Yeah.
Thank you for joining us, Charlie.
Yeah.
All right.
Bye now.